this video, we're going to introduce the concept of partial pressure and then discuss Dalton's law of partial pressure. Okay, so the concept of partial pressure really comes into play when we have mixtures of gases. And so before we jump into this, I want to take a quick minute here to go ahead and recap what we just talked about in the previous lecture, this idea of the ideal gas law. We saw how there are these different relationships between pressure, volume, temperature, the amount of substance, number of moles and volume, and we saw how we could put all these relationships together and get this ideal gas equation, PV equals nRT. And I want to draw your attention to the fact that nowhere in this development did we make mention to a specific type of gas. In other words, this ideal gas law holds for any gas. Now, to be more precise there, it holds for any gas under a certain set of conditions. And we'll talk about those conditions in a future lecture. Suffice it to say, though, if you're at typical temperatures and pressures, this PV equals nRT relationship will hold for any gas. Okay, we don't care about the identity. All right, so then now, with that in mind, let's take a closer look at this concept of pressure. So we know that pressure is defined as a force over area. Okay, so a force over unit area. Now, when you have a gas, and we'll look at the example of maybe a little piston chamber here, a little piston chamber, closed cylinder, and let's say we've got some little gas particles, gas molecules, or atoms flying around inside this container. Each of those little gas molecules that impacts the side of the container, and one of these little molecules come over here and hits the side of that container, it's going to exert a pressure, right? Because there'll be a force of that impact, and then the area, the surface area, the side of that container over which that force is applied. And so when we take a measurement, a pressure measurement of a collection of gas molecules, what we're really doing is looking at the total force exerted by all of those little individual molecular impacts divided by the surface area of that container. Okay, so with this little model in mind, I'd like you to turn your attention to the following little simulation that I have illustrated on the screen here. So what we're looking at is a real-time simulation of a little tiny microscopic piston chamber with all these little gas molecules flying around inside this chamber. Okay? And then what I'm doing is I'm having the computer keep track of every single time one of these little particles, one of these little molecules impacts the side of the container. Okay? When that molecule hits the side of the container, I have the computer ask the question of, well, how fast is it going? And look at to be able to calculate the force, and then divide that by the area over which that impact occurred, and then I'm registering that impact on this little pressure history counter over here on the right-hand side. So notice that every time one of these little molecules hits the side of the container, and becomes more apparent if we shrink down the number of atoms, every time one of those little atoms hits the side of the container, there's a blip right over here on the pressure history. Okay, so the first thing that I want to draw your attention to is the fact that, obviously, if we are, say, looking at the side of a balloon or looking at the pressure gauge on a bicycle pump, we don't see these individual atomic events. Okay? What we actually see is an average of these events. Okay? So if I were to increase the number of gas molecules up to about where it was before, notice how those spikes become more and more common. So there's more and more of these spikes showing up. Okay? And so the idea is that if you have a balloon or if you have a bicycle pump, what you're really looking at is something on the order of Avogadro's number of individual gas atoms or molecules flying around inside that balloon or bicycle pump. And so as a result, here I only have 16, right? But imagine if I had this chamber full of Avogadro's number of gas molecules moving around really fast, And the result of that would be an effective averaging of the pressure. Okay, so when you are looking at a measurement of pressure on a macroscopic scale, you're seeing an average of a huge number of individual atomic events. So to capture that, of course, the simulation is not going to allow us to go much higher. I mean, I think we can take it up to 20, right? But at 20, we're maxing out the simulation. But what we can do is increase the measurement time. And notice that as I increase this measurement time, what I'm effectively doing is introducing that average effect that occurs when we make a measurement on an actual gas sample. Okay? And so this value right here that we're kind of hovering around is going to be very close. We can click right here on this toggle for showing the theoretical value. It's going to be very close to that theoretical value that would be predicted by a simple PV equals nRT type model. Okay, so PV equals nRT is here in black, and we can see once we're averaging over all those little tiny atomic events, all right, then we start to approach that ideal gas value very nicely. Okay, so this is pressure, right? And this is how we can tie this macroscopic quantity pressure down to these individual atomic events. Okay. Now I want you to consider the following question. Let's take off the show theoretical value here, and maybe we can go back down to say 10. Right. I want you to consider now what would happen to the pressure if rather than adding 10 additional blue atoms, what if we added 10 additional red atoms? So you could see we were hovering right up around 1, getting close to 1 on these artificial pressure units. And now that I've shrunk the number of atoms back down to 10, that average is coming back down, and now we're hovering down there about 0.5, right? 0.5 are these arbitrary pressure units. Okay, all right. So now make this prediction. All right, go ahead and pause the video for a second. Make the prediction. What's going to happen if I add in 10 of a different type of gas, say these red atoms? Okay, so same conditions, same temperature, right? The same volume of the container. We're not changing any of those other variables, but we're simply going to add in another type of gas, 10 more atoms. Okay, so hopefully you made the prediction that the pressure is going to go up. Okay, so let's see by how much. So remember, we were at 1 before, right? But we cut it in half. Now we're down there at 0.5. What I'm going to go ahead and do is dump in full 10. Put 10 little red atoms in there. And notice, as these red atoms start impacting the side of the container, then those little blips are showing up in the pressure history. Again, we're taking that full average of all these little molecular events. And we'll notice there's 10 blue and 10 red. Okay? And so as a result, the pressure from each one of these guys, all right, is hovering right about the same value. Okay? Now, if we click down here to say, look at that total pressure, right? What we're going to end up with, right? And if you think about it, we've got individual atomic events occurring that are the result of the red atoms hitting the side of the container, exerting a pressure. Blue ones, same exact thing going on. So the total pressure, it turns out, is summative, right? In other words, if you look at the sum total of pressure of now the 20 atoms, but now 10 of them are red, 10 of them are blue, that total pressure is hovering right around 1, just as it was for 20 blue atoms, just by themselves. Okay? So this is the result. This is the idea behind partial pressure. The container, the side of the container, the pressure exerted on that side of the container doesn't care about the color of the atoms, the identity of the atoms. All it cares about is how many of those atoms are present. And then, of course, what temperature and what volume are also present in that container. So, of course, if we were to change some of those other values, say, decrease the volume, well, we would predict then and you can pause the video, right, to remind yourself, if we decrease the volume, what do you predict is going to happen to that pressure? Okay, so let's go ahead and do it. So the volume's up here. I'm going to go ahead and shrink it back down. We'll go down here. Okay, so notice what's happening to that pressure. When I decrease the volume, the pressure is going up. Well, the reason becomes obvious when we're looking at the simulation. Now, these little atoms are bumping into the side of the container, exerting a force on the side of the container much more frequently. They don't have as much room to move around. So they're impacting the side of the container more and therefore increasing the pressure. Okay. Similarly, if we can move our volume back out here so we can get a better feel for the movement of these little guys. If we increase the temperature, I want you to watch closely on what happens to the motion of these molecules. And before I actually increase the temperature, I want you to make a prediction. What do you think is going to happen, right, to this system, right, in terms of pressure and the visualization if I increase the temperature? Okay, let's go ahead and do it. We'll crank the temperature up nice and high to 400, and you can see right off the bat these little molecules started moving faster and faster. Okay, so I jumped it up to 410 Kelvin, and the molecules really start bouncing around inside of there, so they're moving faster. Well, notice also what's happening in the pressure history. There's another sharp increase in the pressure. Because those atoms are moving faster, they're impacting the side of the container with a greater force. Right? Area remained the same in this case, but a greater force, pressure equals force over area, greater force corresponds to a greater pressure. And notice how in all of these alterations we've made to the system, it doesn't matter whether you're red or blue. Red or blue are behaving exactly the same, and therefore the total pressure is just the sum total of the contributions from both the red and the blue. Okay, so to summarize what we just saw here, right, what we saw is that we could describe the total pressure of this system using the ideal gas equation, PV equals nRT. We're going to solve for pressure. And then we saw how the number of atoms, right, the number of atoms that were present in the container, right, it didn't matter what they were red or blue. We could just add up the total number of atoms to predict the total pressure inside of that container. So if we were to separate this out, we could write this as in blue, I'll abbreviate blue with a B, RT over V, plus in red, RT over V, which is simply the pressure resulting from the blue atoms plus the pressure resulting from the red atoms. Okay, so hopefully in exploring in this way, this is a rather intuitive result. And it turns out that this result right here is in fact what we call Dalton's law. And those pressures that we found for the P red and P blue atoms are what we call partial pressures. So let's put out some formal definitions here. So the first one, partial pressure. Partial pressure is simply the pressure exerted by a given component in a mixture of gases. Okay, so each individual component is going to have its own partial pressure that will be a contribution to the total pressure of the system. And Dalton's law then says that the total pressure of a system, we're going to denote that P tot here, of a mixture of gases, we'll say that there are capital N ideal gases, is simply going to be the sum of the partial pressures for every one of those component gases in that mixture. Okay, just as we saw in the previous slide where we had pressure of the blue plus the pressure of the red equaling our total. Okay, now there's one other concept here that it turns out is very useful when we're talking about these concept of partial pressures, and that is the concept of the mole fraction. Okay, so the mole fraction of a gas, right, is, and we're going to denote that by X sub I, is the number of moles of that gas, which we'll denote by N sub I, divided by the total number of moles of gas in that mixture. Okay, so the portion of number of moles of the compound or gas that we are looking at divided by the total number of moles. So it's this ratio of moles. Okay, it's a fraction. So we call it the mole fraction. Now, we could express N sub I or N total using the ideal gas law to arrive at an expression that puts the partial pressure of that individual component times volume over RT divided by the total pressure times volume divided by RT. Of course, this component is in the same container as the rest by definition here. So as a result, volume is the same, temperature is the same, everything's under the same conditions. So all of those terms cancel out. And we're left with this relationship where the mole fraction is simply the ratio of the partial pressure of the ith component divided by the total pressure. Or, put it in another way, we can determine the partial pressure of a given component of a mixture of gas by multiplying the total pressure by the mole fraction of that gas. Okay, so let's use this mole fraction to solve a following problem here. Let's suppose that we have a gas that's held at 2.0 atm, and let's suppose that it has two different components. It is comprised of 0.89 moles of argon and 0.50 moles of helium. All right, we want to determine what is the partial pressure of just that argon. Okay, so we know total pressure, P total, it's 2.0 atm. Okay, and we know the number of moles of argon and helium. So we're going to use this relationship that relates the mole fraction, number of moles, right, of our given gas, and the partial pressure of that gas using the total pressure. So first up, we're going to solve for that mole fraction. Simply plug in the number of moles of argon divided by the total number of moles, add up the number of moles for both components of the gas, get 0.64. That's going to be our mole fraction x sub I that we'll plug into the equation above here. And then we're going to multiply by the, should be 2.0 atm. And at the end of the day, you'll then arrive with something about 1.3 atm as the partial pressure for just that argon. Okay, so now as a final example, I'd like to take a couple minutes here and work through a rather detailed example of the power of Dalton's law, and look at a more detailed, a little bit more challenging problem that Dalton's law of partial pressures allows us to solve quite directly. So in this problem, we've got a situation where we basically have two glass bulbs connected by a valve. So I'm going to draw these out. So we're going to have one glass bulb right here, and we know the volume, right? We've got the volume of this guy, 650 milliliters, and we know that it's occupied by N2 gas. Okay, so and we can put it into liters, right? And this is also, we are told, held at a pressure of 825 torr. Okay, now we're told that this bulb is connected to another bulb, right? And there's a little valve there in between. And this other bulb, right, is full of oxygen gas. And we know that the pressure of that oxygen gas here is 732 torr, and the volume of that oxygen gas cylinder is 0.5 liters. Okay. Now, we're going to suppose that the valve is opened and that the two gases mix. And we need to calculate the total pressure and the partial pressures of the N2 and O2 in the resulting mixture. And we're going to assume a constant temperature throughout this process of 298 Kelvin. Okay, so to write out and give ourselves a little bit more room here, we're going to take this setup, and our goal is to find the total pressure and the partial pressures of each one of these gases. Now, of course, once we have both of these partial pressures, we can use Dalton's law of partial pressures to get that total pressure. Okay? So really, if we can get to the final partial pressure of N2 and O2, then we'll be home free. Okay, so in order to do that, I encourage you guys to go ahead and stop the video now. We're of course going to be using Dalton's law up here, but in order to do this, we're going to have to go back and use what we've already learned about the ideal gas law. So I want you to pause the video here and go ahead and try and work through the rest of the problem and see how far you get. And then once you either get a solution or get stuck somewhere, then go ahead and press play again. Okay, so for solving this problem, what we're going to do is go ahead and use PV equals nRT. We know that we're at 298 Kelvin. Okay, so we're going to use PV equals nRT to solve for the number of moles of each of these gases. Okay, so we'll write out an expression, again, just looking at the initial conditions here. Okay, so we'll make note of that. So looking at just the initial conditions here, we're going to use what's given in the problem to figure out, before we do anything else, how many moles of each type of these gas molecules do we have. Okay, so plugging in the values, we have, okay, I'm going to went ahead and converted these pressures in torr into ATM. Similarly right here. Convert those to ATM, plug in the rest of the known quantities, and we should arrive at numbers of moles equal to 0.02887 moles of N2 and 0.01969 moles of O2. Okay, now that we have the number of moles of each type of gas, we've got a couple options. So one option is that we could use this number of moles, and we can use the fact that at the end of the day, we know the volume. We know that the volume, the final volume, is going to be the volume of that N2 containing bulb initially and the O2 containing bulb initially. We're going to add them together, and we will arrive at a value of 1.150 liters. So the final volume is essentially given to us in the problem. And we know, of course, that we're staying at this constant temperature. Okay, and so if we know the total number of moles that are present, right, which is just going to be the sum total of what we have right here by adding together the N2 plus O2, we can arrive at our total number of moles, and this will give us a direct solution for that total pressure. Okay. Now, of course, we could solve for the partial pressures first and go back to the total pressure. Either way is fine. We'll go ahead and take that total pressure value by first figuring out the total number of moles, adding together number of moles of nitrogen, number of moles of oxygen, right, to get this value of 0.048565 moles. Then we're going to plug this into our expression for the total pressure. Right? Total pressure is going to be total number of moles we just found times RT over that final volume after we've mixed everything together. Right? So we're going to plug in these values, 8565 moles. We know R liter atmosphere mole Kelvin. Give myself a little more room here. Okay, so I move it over a little bit. And so we plug in our temperature, our fixed temperature of 298, take that final volume that we determined by just adding the volume of the two different bulbs together because they're now connected, and then plug in that final number of moles. all right, total number of moles of both gas molecules. Put it all together, we get a value of 1.03 atm or 748 torr. Okay, now I'm going to leave it as an exercise for you guys to go ahead and use the mole fraction to determine the partial pressures of each one of these components into an O2 and the resulting 1.15 liter container. And you can check those answers. So you should get a value, as we saw here, we've got 748 torr for the total pressure. You should come up with values of 466 torr for your nitrogen and 318 torr for the oxygen. Okay, so to summarize what we've talked about here, we've seen how all gases are created equal in the eyes of the ideal gas equation. So it does not matter the identity of the gas. If it's behaving ideally, we don't care. The fact of, this fact led us to this Dalton's law of partial pressures, which says the partial pressure, which is the pressure exerted by a given component of a gas mixture, added up for every single component is going to give us the total pressure for that mixture. And we saw how we can use this equation to help us solve a couple examples. And of course, we introduced this concept of mole fraction as another helpful tool in discussing and examining this relationship between total pressure and the pressure of a given component, the partial pressure of a given component in a mixture.